Alrighty, here we are. Again, it is Tuesday, November 17th, 2020, and today we're talking about probability rules as a broad topic. First thing, probability models. Probability relies on the fact that chance behavior becomes predictable over many repetitions in the long run. This is what we've discussed last week in section 5.1 of the text, right? Probability depends on long-run outcomes. Fortunately, there are ways we can determine the probability of a particular outcome without repeating a chance process over and over and over again, right? So there's other tools besides simulations, which still can be very time-consuming and difficult to set up, depending on the number of things that could happen, where we can use a probability model instead. To do this, we use probability models. These consist of a list of all possible outcomes. We call this the sample space, and it gets the letter S. In some other textbooks, they might use the Greek letter omega. That's what my probability textbook used for college. It's fine. S is very common as well, and so that's what we're going to use because that's what our textbook uses. And a probability of each outcome. All right. So what we're going to look at today, everything within our outcome space has an equal probability or equal likelihood, which these are the most basic forms that we can look at. Here's our definition of sample space and probability model from the textbook. The sample space S of a chance process is the set of all possible outcomes. Probability model is a description of some chance process that consists of two parts, sample space S and a probability for each outcome. All right. Can you raise your hand if you need a little bit of time to write any of this down? So we have sample spaces. Sample spaces can be very simple or very complex. For example, when tossing a coin, there are two possible outcomes, heads or tails. And we can represent this sample space with the notation S equals H, comma, T. There's only the two possibilities. There's our sample space. When drawing a random sample of 1,523 adults, of the 235 million adults in the country, right? And we're trying to answer survey questions, so it's like a, I don't know, there's like a census survey, something like that, right? The sample space contains all possible sets of responses from 1,523 of the 235 million adults in the country. This S is extremely large and complex to the point where like we can't really visually represent it at this point. So they go from really simple, two options to, I mean, millions and millions of options. Oops, sorry. Does anyone need a moment for anything on this screen? So let's look at an example of a sample space. So what we're going to do is we're going to set up a probability model for rolling a pair of dice and all the different outcomes that are possible. To do this, rather than try to write on the PowerPoint, I'm going to use OneNote because it seems to cooperate better with my little stylus thing. So here we have our kind of setup here for our sample space. We have this grid set up here. And the row here, or that means the column, 1, 2, 3, 4, 5, 6, represents the possible outcomes for a red dice, or red die. 1, 2, 3, 4, 5, 6 across the top here in the first row represent the possible numbers that we could roll on a green dice. So we have a red dice and a green dice. S is the sample space, which represents the outcomes of rolling two dice, all the different possibilities. All right, there's 36 possible outcomes that are equally likely to occur, meaning each one of these squares has a 1 in 36 chance of happening. all right? Because these are fair dice. There's 6 possible outcomes for the green dice, 6 possible outcomes for the red dice, which means 6 times 6, 36. We have that 36 possibilities. All right. So when we roll 2 dice, right, 1 number will be contributed from the green dice, 1 number from the red dice. So like in this first square, we would get the outcome of 1 and 1. Right, the next one would be 1 from the red, 2 from green, and so on. 1 from red, 3 from green. We're just listing all the different combinations that could happen. That's what our sample space consists of. Okay, so we'll go through and fill this out. Oops. Now the advantage of a sample space like this is it makes it so I can actually just count up the things that I'm looking for when I'm trying to determine a chance or probability of that specific outcome. Final. All right, so here's our sample space. So now I could say, okay, based on this sample space, what are the chances of rolling a 1 and a 5? Right? So what we would look for is just any combination of 1 and 5. And what we would see is we get 1 and 5 here. We have 1 box. And we have, I made a mistake. I put 2 rows, a bunch of rows of 4s. What? What'd you guys let me do that for? Can't believe I did that. Sorry, guys. Hold up. Mosley made a mistake. Oops. See, mistakes are okay as long as you catch them. All right. And 5, 6, 5, 6, 5. This works much better because it's correct. All right, here we go. Here's our other option of getting a 1 and a 5, right? We have 5 and 1. There's 2 possibilities. There's no other way. A red 1 and a green 5, or a red 5 and a green 1. So I have a probability, or chances, is 2 out of 36. All right, we could do chances of a sum greater than 10. So what are the chances that the sum of my 2 dice is greater than 10? Well, where do we hit greater than 10? We have 5 and 5, 4 and 6, 6 and 4, 6 and 5, and 6 and 6. So these combinations of dice rolls satisfy this thing that I'm asking for, right? Chances of a sum greater than 10. Oop, that's not true. We only want greater than 10. right? We're equal to 10 at 6, 4, 5, 5, right? So then we only get these 3 possibilities that are greater than 10. So again, we have 3 out of 36. Right, so this sample space allows me to visually find the result I'm looking for, and then I can count how many things satisfy what I've been asked. Right. Are there any questions, comments, concerns, clarification? We'll have an opportunity to practice with this later on. Okay. All right, so back to the PowerPoint. So here's another representation of the sample space. This would take much more time to draw, so I don't want to draw dice and the dots and all that fun stuff. This is another representation of the same sample space. Based on our sample space, which is this one or the other one that I drew, right, a probability model allows us to not only see all the outcomes, but we can also find the probability of any collection of outcomes, which is called an event. Right. So the scenarios that we found solutions for on the OneNote page, those were events. Right. If A is an event, then its probability is written as P parentheses A, right? Probability of A. And the book defines an event. Right? An event is any collection of outcomes from some chance process. That is, an event is a subset of the sample space. Events are usually designated by capital letters like A, B, C, and so on. Right? So an event has to be something that could occur within our sample space, right? Or at least has to do with the things we're talking about. It is possible to have an event that has a probability 0 within your sample space. It's also possible to have an event that has a probability of 1 within your sample space. Okay. Next. So lit event A in the sample space you defined as the sum of the 2 dice is 5. And event B be defined as the sum of the 2 dice is not 5. So whatever is a different sum. What is the probability of A? And what is the probability of B? Right. In our sample space, we see that there are 4 outcomes where the dice have a sum of 5. Got them circled or boxed here. There are 36 possible outcomes, so the probability of A equals 4 out of 36. We can reduce that fraction to 1/9, or even have an estimate of the decimal of 0.11. It is recommended and more common to just keep the first fraction here, the 4 out of 36, because it preserves the number of possible outcomes, right? So you don't always have to reduce the fraction or simplify the fraction in these cases. It's kind of nice to just keep it with the base, the denominator that represents the total possible number of outcomes. So keeping 4 out of 36 as the result is actually preferred. All right. We're trying to find the probability of B. It's a lot of other things to count, right? We know the probability of A plus the probability of B, right? The sum of the 2 dice being 5 and the sum of the 2 dice not being 5 covers all of our outcomes. So that equals 1. So the probability of B is equal to 1 minus the probability of A, of 1 minus 4 out of 36, which gives me 32 out of 36 possible outcomes. That represents the probability of being not a sum of 5. Okay. Again, that could reduce to 8/9, but it's typical to just leave it with the denominator as the total number of outcomes. Is there anything I can clarify? Can you raise your hand if you need a moment to write any of this down? So this leads us to our basic probability rules. Number one, the probability of any event is a number between 0 and 1. This goes back to our original definition of probability, right, on that scale from 0 to 1. All possible outcomes together must have probabilities that add up to 1. Otherwise, we forgot something. If all outcomes in the sample space are equally likely, the probability that event A occurs can be found using the formula. P of A equals the number of outcomes corresponding to event A divided by the total number of outcomes in the sample space. Exactly what we did in our example with the dice, right? There was 4 number of outcomes corresponding to our event, right? Sum of 5, and we had that over divided by the total number of outcomes. Number 4, the probability that an event does not occur is 1 minus the probability that the event does occur. If A is the event, then not A is when the event does not occur. We refer to this event as the complement of A and denote it as A superscript C. Okay. A complement, or the idea of a complement in mathematics, shouldn't be brand new, but it's something that goes through other areas of math. You've probably only seen it in geometry, where angles have complementary angles, right? And that is essentially the rest of the complement, I think, goes to 90 degrees. I don't remember. I always get those backwards. I always have to look them up. But essentially the complement is everything else except that thing, right? It's what we would have to use to complete the rest of the sample set. Okay. So we have a complement and we have a notation for the complement of a specific event. And number 5, if 2 events have no outcomes in common, the probability that one or the other occurs is the sum of their individual probabilities. When 2 events have no outcomes in common, we refer to them as mutually exclusive or disjoint. Okay. So an example of things that are mutually exclusive is if we look at the dice example, rolling 2 1s and 2 6s in the same roll. Those are exclusive or disjoint events. I can't have both of those rolls show up in one roll of the dice. I can have one or the other. I can't have both. So those are mutually exclusive events. Can you raise your hand if you're writing these down and would like some more time? Okie dokie. So then this is a graphic that kind of shows those basic probabilities with notations rather than just all the words. So we have for any event A, probability of A is between 0 and 1. Right, so 0 is less than or equal to the probability of A, which is less than or equal to 1. If S is the sample space in a probability model, the probability of S equals 1. Right, that's just saying that the sum of all possible outcomes equals 1, as far as the probabilities go. In the case of equally likely outcomes, probability of A equals the number of outcomes corresponding to event A divided by the total number of outcomes in sample space. The complement rule, probability of A superscript C So the complement of event A is equal to 1 minus the probability of event A. Then we have the addition rule for mutually exclusive events. If A and B are mutually exclusive, the probability of B or the probability of A or B occurring is equal to the probability of A plus the probability of B. We have to pay attention to the word here. P of A or B is not the same as P of A and B. Those are completely different things. We'll see an example of this in a little bit. Right. If you're writing these down and would like a little bit more time, can you please raise your hand? Okay. All right, so here's where we're going to go next. We're going to do some practice with this. So we're going to do a Pear Deck. We're going to do some examples using our sample space of the rolls of the dice to find different probabilities. All right, so here we go. Question number 1, use the dice sample space below to determine the probability. We have probability that the sum is 7 of the 2 dice. What is that probability? I'm going to give you all 2 minutes to respond. So, here we go. Here is our solution. All right. So the answer here, the probability that the sum of the 2 dice is 7, is 6 out of 36. All right. This is just asking for the probability. We didn't need to list all of the outcomes that fulfill that event. We just wanted the number. We wanted the outcome, or wanted the probability. All right. So I have them kind of put in a box here. We have 1, 2, 3, 4, 5, 6 possible combinations of dice rolls that add up to 7. You guys have any questions about how we got this? Or why it's 6 or not a different number? Okay. Let's try another one. So now what is the probability that the sum is 7 or the sum of the 2 dice is 5? Again, we're going to give 2 minutes here to get your responses. Here's our solution. The probability that the sum is 7 or the sum is 5 is 10 out of 36. Right, if you reduce that, it could have been 5 out of 18. Right, and we see that because we have the 6 options that we saw for the previous question, the sum of 7 that we still get to have. And then we add the 4 possibilities that account for the sum being 5, right? 4 and 1, 3 and 2, 2 and 3, 1 and 4. All right, that totals 10, right? This is an example of events that are mutually exclusive or disjoint, right? There's no pair of dice that sum is 7 and its sum is 5. Okay, so they are mutually exclusive. So when we want the probability of one of those 2 events happening, the or situation, we add the probability of each of those events, which is 6 out of 36 plus 4 out of 36. Anything I can clarify? Okay. On screen, catch up. There it is. All right, so now let's consider the situation where we want to know what's the probability that the sum of the two dice is 7 and the sum of the two dice is 5. So in this case, these events are disjoint, right? So the probability of both of them occurring in the same time is 0, right? I can't make the two dice that add up to 7 also add up to 5. So the and in mathematics typically means that both things must happen to satisfy the situation. Right? Or says either of these things can happen to satisfy the situation. So we consider or to be inclusive and to be exclusive. Right? So they have, it's different than how you would typically treat or an and in like an English class, so to say. Right? Or is inclusive and is exclusive. Right? So we can kind of, I'm going to draw a picture to make more sense of or and the difference. So we're going to look at this here real quick. So the best way that I can think of to explain the difference between and or is to use a Venn diagram. If you guys are familiar, a Venn diagram is where we have the, like at least two circles. You could have more, right? And they have a little intersection area. All right, so we'll call this one A and this one B. And then, so now between these things, we have different things that could happen. Right? We're looking at the probability of A or B versus the probability of A and B. Okay? P of A or B is anything within A or B happening satisfies this probability. In this case, because I only have events A and B, that's the entirety of my sample space. That's equal to 1. Because that's everything. I don't have anything else. Okay. No. Yeah, I can draw this differently so we can have different, I'm not going to get that. Never mind. P of A and B is where both A and B are happy. They're both satisfied, right? It's what they share. It's the intersection. So the probability of A and B is just this yellow highlighted section, right? So that probability would be whatever that is over the total possible number of outcomes, which we're just looking at it over 1 right now. Well, let's do it this way to make it a little bit better. Nah, never mind. But anyway, we have our intersection is that shared amount. When we look at our example here in this last problem, there's no shared area, which means their intersection is empty. So the probability of having something shared, something in that intersection, is 0. Does that help, or did I just make it more confusing? Okay. So then here, if we look back at this, our sample space scenario, let's say that we want the probability of a sum of 7 and say a sum of 7 and a green 3, right? It's very specific. So then we can go through and say, okay, we know we have the sum of 7 is this diagonal. And then we have a green 3 is this column. So the probability of having a green 3 and a sum of 7 is the intersection, which of the two things where we have that is just here. There's only one possibility that fulfills that. Hopefully this makes a little more sense. So let's get back into it. So now, last question here. What is the probability that the sum is not 7 or 5? Now we're looking at the complement of the sum being 7 or 5. So here we go. The probability that the sum is not 7 or 5, which is the complement to the sum being 7 or 5, is 1 minus the probability of the sum being 7 or 5, which is 10 out of 36, which leaves us at 26 out of 36 for the probability. Right. Any questions on this last one or any of the previous examples? Hopefully this helped make a little bit more sense about probabilities and sample spaces for today. I'm going to end this. And do a quick look at week 13, which is our current week. There will be a discussion board for after class today. We have our live class resources. Those will be updated shortly. The discussion board. Is right here. We have two events, A and B, being represented here. And you're asked some questions about probability of A, probability of B. The probabilities of those two events are provided. And getting answer some questions based on our probability rules and what you know about probability so far. Hopefully this makes a little bit of sense based on the activities we did today and the lesson. But as always, if you have any questions, please ask. I'm happy to help. Send me an email. Ask me right now. Put a chat in the Teams on any of those. So that's going to be the assignment for today. And then there will be a weekly, like a CYU, like a little quiz for this week, and one more discussion board, and that'll round out the week. And then you have next week off. All right. And so that sums it up.